Okay, does anyone have any questions about what we did last time? Thermochemistry, determining the enthalpy of a reaction based on the bond energies, based on the enthalpy of formation, based on Hess's law, where we did the reactions. Can we please go over thermochemistry and do an example? Okay, so I think I have, I'm just going to use the study guide, Dr. Pappas' book, to do that, okay? And go from there, okay? So we are into thermochemistry. I can't remember. I gave you some review questions, but I don't remember where that is. Let me go ahead. Can I have a volunteer to let students in? Can I have a volunteer?
I don't remember.
Thanks, Maria. I'll let you do that for me. Let me do it right now. Okay, so I did that. Thank you so much. All right, so I'm going to try to find see where I can share. Okay. I'm looking for the stuff that I gave you guys with thermochemistry. It's not here. I did not open that one. Thanks. Thermochemistry. So I'm going to use my notes and examples to help you guys go through that very quickly. Okay, so we did, are you guys seeing this? You should be seeing this. Okay, let me see where I am. Okay, I'm sharing. Okay, so if you look at these notes I just opened it up from your course. Yes, so we talked about thermochemical equation. And we said we had exothermic, endothermic. Okay, so what we do here, we have reactions. And what we do here is you will be given an equation, and if it has delta H equals negative, that means it's an exothermic reaction. If it's positive, it's an endothermic reaction. What you see here is that you can manipulate thermochemical equations by writing it in the reverse direction. So if you see right here, we were given this. If I reverse the reaction, the enthalpy of the reaction changes. Okay, what's important in thermochemistry is the states of the substances. Okay, because if I had carbon as another form, my enthalpy would change. Okay, so that's what this is showing you right here. So when you look at your enthalpy of your reaction, when you get to 46, the states are going to matter. Whether I have carbon dioxide as a gaseous form or has a solid form. Okay. And something else you see here, if you look back at this note, it says if I multiply my equation by a coefficient of 3, make it 3 moles, then the amount of heat that is absorbed or released is multiplied by 3. Okay? With thermochemical equations, we can have halves or we can have fractional coefficients for my thermochemical equation. So if I had taken 1/3 of this equation, then it would be divided by 3. Okay, so that's what that is. It says down here, this is a summary. States are important in thermochemical equations. When you see your thermochemical equation, it will and they give you the delta H, it will be kilojoules per mole. So this particular equation is the decomposition of carbon dioxide and water of 1 mole of carbon dioxide will involve the absorption of this amount of heat. Positive means endothermic, it means it's absorbed. Okay, so the next thing I did with you guys last time was I talked about stoichiometric calculations involving heat. When we did stoichiometry, we didn't talk about the heat because reactions don't just occur just like that. In most reactions, we have to provide energy, which means give it heat, or the reaction will take place and it will give out heat. It's an exothermic reaction. So when we do this here, this says 1 mole of methanol reacts to produce 764 kilojoules of heat. I said produce because it's negative. The question that you're going to be asked depends on what is it. It says find the heat evolved. The word evolve means that the answer should be negative. So it does not, when you solve this equation, you do not need to put the negative because the question asked you about evolved. Okay? So if it says what is the enthalpy of the reaction, then you have to put negative. But it says find the heat evolved when you have 115 grams of methanol burning in excess oxygen. So here we go. In this particular question, and I think I have the answer down here. If I look at the equation, this says 1 mole of my reaction, yes, will produce 764 kilojoules of heat. Okay, so what am I going to do? I am going to say here, I'm going to take my grams, convert it to moles, then use the relationship from the balanced equation. So my delta H comes in as part of my products of my reaction. Okay, and that's what we did there. So you might get questions where they'll give you grams and they ask you how much heat is evolved or absorbed. And if it uses the word evolved, absorbed, then you do not put the negative sign. Okay, and sometimes the multiple choice question will come with positive and with a negative number. Okay, so if it's positive, they'll put plus. If it's negative, they will put negative. Okay, now this question says, if we go back up a little bit, it says what mass of oxygen is consumed when 925 kilojoules of heat is given off. So it's telling me it's already negative, so I don't have to use it. In my equation, this says 1.5 moles of oxygen would cause the evolution or giving off of 764 kilojoules of heat. So I used the what's given, and I used it to find the moles of oxygen, and then I went to find the grams of oxygen. So that's basically what we do. Okay. I'm going to go on down. I'm going to go down to the section there where we talk about standard states and enthalpy changes. Now, when we do a reaction, you will see in your questions, they will give you delta H0 of a reaction. And that is the standard state of enthalpy changes. When you did gases, you knew that it was 0 degrees Celsius and 1 atmosphere. Now it is 25 degrees Celsius and 1 atmosphere. This is the thermodynamical standard conditions. You're going to need to understand that when you get to 1046. Okay, so they can do reactions at other conditions, but if it has the 0, it will be done at 25 degrees Celsius and 1 atmosphere. So that's what we do there. Okay, so we can have enthalpy change. When you see this here, this is the enthalpy change for the formation of 1 mole of your substance. Okay, so down here, this question is asking us, this equation here says 1 mole of hydrogen reacts with 1 mole of bromine gas to produce 2 moles of hydrogen bromide gas. The delta H of this reaction is negative 72.8. This is not the delta H of formation of HBr, because the delta H of formation, the enthalpy of formation is the formation of 1 mole of the substance from its constituent elements. So the delta H of formation is for 1 mole. So my equation for 1 mole would involve a fraction, half a mole of hydrogen plus half a mole of Br2 liquid will give me HBr. And I wrote here, it would not be the same if Br2 was a gas. Okay, so this is the enthalpy in liquid form. Bromine exists as a liquid in natural at room temperature. So that's why we have it like this. I'm going to skip over these questions. They're done for you on the course site. Okay, so I'm going to skip over these questions. Okay. So it says delta H of reactions involve physical processes, mental freezing can be predicted. Combustion reactions are usually exothermic. Physical changes, solid to liquid, liquid to gas. Most times we need to take in energy to change it. We can explain why. The reason for that is because if you look at remember when you did solid, liquid, and gaseous states, you said your solid particles were close to each other. Your liquid particles are far from each other, and your gases are even further from each other. I remember one of your classmates asked me, will phase changes always be endothermic? And the answer should have been yes. I did not say yes because I was thinking about a lot of other things that I did not want to answer incorrectly. So if you change from a solid to a liquid, or a liquid to a gas, or solid to a gas, it's going to be an endothermic process. And the reason for that is your particles are close to each other, and you need to have energy to break the attraction between those particles. And for those of us going into 46, that's where you're going to start. You're going to talk about intermolecular forces, the forces that hold your particles together, your molecules, your atoms together. So you're going to start there for those of us going into 46. Okay, so we can determine the enthalpy of a chemical reaction. When you get to 46, you're going to do the energy or the enthalpy change, how much heat is released by reaction. We're going to do calorimetry. Okay, remember when you did at the beginning, you did Q equals M times S times delta T. That Q was the enthalpy that we're talking about here. Okay, so when you get to 46, we're gonna do it a little bit different, where when we do calorimetry, we do it in a container. And normally we think about the container will absorb some heat, but most times we don't think about that. We do it without. So that when we get further into the chemistry, we are going to look at calorimetry. So we can determine the delta H by Hess's law. This is what we did. It says if a reaction is carried out in a series of steps, the delta H of the reaction is the sum of the enthalpy changes for the individual steps. Remember, I tried to do that last time. I need to apologize last time because when that professor called me to get some help, I really got flustered and I messed up quite a bit, in my opinion anyway. Okay, so let's look at this question. The formation of carbon monoxide is not something that we know, yes, but we can determine the formation of 2 moles of carbon monoxide by using stuff that we know. We know that when carbon graphite reacts with oxygen, it produces carbon dioxide and it gives off that amount of heat. And when carbon monoxide reacts with oxygen, it will produce carbon dioxide here. And the enthalpy change for this reaction, it's this. This is what we did last time. We can use these 2 equations to determine the enthalpy for this reaction. How do you do that? You are going to get one of these. I'm just telling you up front. Let's see, I see a chat. Let me see what I should be looking at. Okay, that's what I'm doing. Okay, so what do we do when we get questions like this? We look at what's being asked. We look at where the reactant is, yes? Sorry, the product, and see where it is in the 2 equations given. So, okay, this is here, yes? So this is on the reactant side. So guess what? I need to reverse this reaction B right here. And if I reverse it, then this becomes positive. What do I mean by reverse it? Say if 2 moles of carbon dioxide decompose, to give me CO and O2 that will need to take in energy, so my delta H will be positive. So I need the carbon monoxide on the product side in the equations given. It is on the reactant side. Now, what do I have here? I have no carbon dioxide in there. If I reverse this one, I now have CO2. So if you look at my work, I said I'm going to multiply the first one by 2. Multiply it by 2. That means everything. I'm going to multiply the delta H by 2 as well. Okay, and I'm going to reverse this one. When I reversed it, I should have had a line here. If I add it together, remember you remove common species. So when I add it together, I get 2 carbons, 2 oxygens, 2 CO2. The 2 CO2s are gone, and one of the oxygen disappears. And this is what I end up with. And this is the reaction I'm looking for. Okay, so because when I did that, I did this manipulation, I end up with the reaction I'm looking for. Remember, I am manipulating not only this, but also this right here. What did I do? I use this as it is. I multiplied it by 2. And for the second one, I reversed the reaction, which means I changed the sign. Okay, and that's how we end up with our answer. Of course, I did not write the answer. Okay, so you can do that. That's how you would get your enthalpy for the reaction, a question similar to this. Any questions? So you know you're going to have at least one of these. I'm just being honest. Okay, it's thermochemistry, and we're looking at the thermochemistry situation here. And this was another example that I think I did it in here. I'm not going to go through doing this because I want to use the time to maximize, to review as much as possible. Okay, so the information, how we do it, it's there. Yes, okay, that was another one. Okay, we can find the delta H of the reaction from standard enthalpy of formation. We talked about that last time. When we have the standard state of gaseous substances, the delta H list that they will give you, the delta H of formation of elements in their natural state. Hydrogen as a gas, bromine as a liquid, chlorine gas as a gas, sodium as its metal form. It's going to be the delta H of formation at 0 degrees Celsius and 298 degrees Celsius and 1 atmosphere, it's 0. To find the delta H of a reaction, we use the balanced equation, and the delta H of the reaction will be sum of the delta H of formation of all the products in the reaction minus the sum of all the formation of the reactants, where N represents the coefficient. So if I have 2 moles of something, then I'll multiply the delta H of formation by 2, because your delta H of formation is for 1 mole of your substance. Let's see if I have an example down here. It said I was to use the values of delta HF to calculate the delta H of the following reaction. So if you get a question like this on the exam, I will be giving you the delta H of formation that you need. I will give you the delta H of formation of my, close my email out. Okay, so what we do here is we are going to look at that. So when I use the table, I would find, so let's look at this one down here. Let's see, did I do it? Okay, so here in this particular one, I went to the table. The format of your equation is 6 times the delta H of formation, delta H water in its gaseous state. And I'm going to show you the table that it matters, like I did last time. I do believe I did, that it matters. It matters whether I have water in the gaseous state or the liquid state. If you look right here, Yes, the first column is your delta H of formation. You notice they have delta H in the liquid form and they have it in the gaseous form. Yes, so I need to make sure I choose the correct one. Yes, okay, so that's what that is. So let's go back to what we were looking at. Where was I? I was right here. Okay, all right, so this is what we have. So we have delta H in the gaseous format, and it's 6 moles, so it's 6 times whatever that is, plus 2 times HCN, whatever that is, yes? And I sum all that together, minus, now I have 2 times ammonia, 3 times oxygen, plus 2 times CH4. I wrote it like that so we know that delta H of formation of the element in its natural state is 0. If you go to the table, it's not going to give it to you. You will sum that up, you do your subtraction, and if you do it properly, you are going to get your answer. Okay? So that's how we would do that in terms of formation. Now, sometimes they will give you the delta H of the reaction. So this is the delta H of the reaction. Sometimes they'll give you the delta H of the reaction and they ask you to calculate one of these in here. They could have given me this and asked me to calculate one of these in here. Again, it's an equation, so we can go ahead and you guys know how to solve equations, okay? Then the last thing we did was from bond energies. When we have reactions, basically what we're having is the breakage of bonds and the formation of bonds. To break a bond, we need to give energy. The energy to break a bond is going to be a positive number. To form a bond is going to be it's going to end up being a negative number. So here we go. So what do? Bond breaking is an endothermic, bond forming exothermic reaction. So we can look at what we call bond dissociation energy to get the delta H of a reaction. This particular situation applies to gas phase reaction. So when we look at it, the reaction is going to be in a gaseous phase. Okay. So let's look down here, it says use bond energies listed, and I think I ended up giving that. To estimate the heat of the reaction, the enthalpy of the reaction at 25 degrees Celsius. So here, what's important here is that we recognize whether we have single bond, double bonds, triple bonds. Yes. So in this one, HCN, the bond is a CH and a C triple bond N. And in my hydrogen, each hydrogen has a H. So for this reaction, the delta H of the reaction using bond energy is broken, which is reactants, minus form, which is products. So you do that. And students will say, oh, professor, I can keep the H's. You look at every bond in your reactant that gets broken and you break it down to what gets formed in your products. Yes. And you do that. So it's reactant. So in my reactants, I have 1 CH, and this is the number from the table. If you get this, they will give you the bond energies. Yes, they will give you the bond energy for your C triple bond N. So you have, this is the reaction you're looking at. So you have 1 CH being broken, 1 C triple bond N being broken, and you have 3 HH bond in the reactants. In the products, CH4, I have 4 CH bonds. It's the same as HC, it's a single bond, yes? And I have NH3, so I have 3 NH bonds. I add them up and I do my subtraction, and that's how we get that. Okay, so that is doing enthalpy of reaction from bond energies. So they could give you something like this, yes? And they could have asked you, they could have given you the delta H of the reaction and ask you what is the energy required to break this bond. What it would be, you would have this, you would have your delta H and one thing would be missing. Okay, so you can do that. It's a simple algebraic equation that you can go in and look at. So those are the things that, okay, see, this is one of the questions. So it says the delta H of this reaction is negative 153 kilojoules. Given that the HH bond is 400, energy is 432 kilojoules per mole, the oxygen bond energy is 467 kilojoules. Estimate the bond energy for the O single bond O bond. Hydrogen peroxide, it's like this. This is the structure of hydrogen peroxide. So you have OH bond, and they're asking you to do something about that. So when we went in, we saw where I didn't put something else here. I should have given something else. So my delta H of the reaction is bonds broken, which is the H, which is bonds broken minus, and this is an error. I think I did an error here. I had to correct this one. So it's bonds broken, which is HH bond plus OO bond minus bond formed, and we'll work on that. I think I gave the correction to this online. Let me see if I have it here. Correction to written notes. Okay, so in the course, I gave the correction to that particular question. Okay, so if you look at what I have there, you can see that it's incorrect. Okay, so I made the correction there. Okay, so that's basically how you do bond energy. It would be broken minus formed. Yes, okay, so that's what that is. So that's my summary of thermochemistry. Next. Anything else I can help you guys with? This is the list of topics that I gave you guys. Yes. You will have 40 questions. If you looked at your emails, and I'm hoping that you guys did, okay, this is the email I sent out to you guys. Yes. So let's get it down pat. Of course, I was having a problem with dates from yesterday. I keep putting the wrong dates in the stuff. But anyway, we're meeting tonight. It should have been 7:27. Yes. On Thursday afternoon, we are going to meet at, I'm going to allow the exam to open up at 5:30. So maybe you can tell your if you work, you can say, hey, I need to get ready for my exam at 5:30. Hopefully you don't have a class before. Okay. So just like I suggested last time, you get your computer ready, make sure your lockdown browser is working very well. At 5:30, you will have your Blackboard open. 5:30, you click on the course, that exam is going to show up in the assessment area. Yes, you go in and you do what you have to do. Guys, we need everyone to be into the exam by 5:50. Class starts at 5:40, so that will give you enough time to get in if you can't get there at 5:40. Okay, so after 5:50, if you cannot get in by 5:50, you need to let me know, because guess what? At 5:51, the exam is not going to show up. Yes. So this is basically helping you to make sure you don't panic, all that stuff. I will be in the office room to help with whatever you need. So if you have an issue, email me quickly, or office room, professor, I'm on the road, I'm caught in traffic, I can't be there for this time. I'm not going to be very lenient because I'm telling you this. Okay, so that's what it is. If you have issues getting into the lockdown browser, do not spend 15 minutes trying to get in there. Okay, if you're having issues, obviously something is going on. And my suggestion is to use your phone, get into my office room, then you will be able to turn your phone to your computer and show me what's going on. And more than likely, I can talk you through whatever is happening. But if your lockdown browser is taking a long time to log you in, you need to probably get out, shut the computer down for a minute or two, go back in. That's why I'm suggesting you get into the lockdown browser early. So at 5:30, you are there. okay? And you can get into the course itself. So this is basically what it is. You guys did pretty well with the video, making sure you show the video and all that stuff. You can only have blank sheets and non-graphing calculator, as it says here, and please remove the cover. So when you do your environmental video, guys, show me, Professor, here's my paper. You can talk to me in there. That way I know your microphone is working. You need an active microphone as well. Here are my papers. Here is my calculator. Remove the cover, guys, and put it aside, because you know we can put things in the covers, and we know that. Make sure you don't have your AirPods in your ears. Students have done that and end up not getting a grade. Okay, little things like that. You want to make sure you know that you do that stuff. Okay. So another question I have. Go ahead.
Sorry, I just had a few questions, but I can wait until you finish. Sorry.
Yeah, I'm gonna finish in a few minutes. Yeah, I promise. Okay. In 2 minutes, I'm gonna be finished. Okay. So you are going to your ID. Students are using the driver's license, but they have it so far, I cannot make sure that it is who you are. So remember, you don't show me your videos here, so I don't know what you look like. Yes, so I need to be able to see your ID. So if you're using a driver's license, guys, put it close to the webcam or something so I can see it. Yes, I need to be able to see that's the person taking the exam. So that's basically what I have here. Yes, if you happen, this is the part I want to do. If you've started your exam and you lose internet or your power goes off, or hopefully not, I hope not, okay, you can use your phone to get to me. Yes, so you can, okay, this was somehow show me what's happening. I spelled incorrectly. Okay, so that's what it is. So if you get kicked out of the exam in the period, do not panic. Got the computer on, go back into the lockdown browser, send me a quick message, Professor, I got kicked out. I will make sure that the exam is visible. You can get back in because your time is still running. Okay, because you get kicked out, it doesn't mean that it shuts your exam down. You still have an hour and a half to finish the exam if that is so. So that's the idea I wanted to share with you guys. I sent this by email so you guys can do that. On Thursday, no physical periodic table. That's correct. That's gone. No physical periodic table. The exam will have the link to the periodic table, and it will also have it at the very top of the exam. Okay, no physical periodic table, please. Okay, all right. Okay, so let's go back to our list of questions. Okay, anybody has anything they would like me to look at on this list?
Professor,
go ahead.
Could we go over how to do a molecular orbital diagram for a heteronuclear molecule?
Okay, that's a good suggestion, but I'm not going to do it because I'm not going to give you anything.
Oh, okay. And I was also wondering about how do we know if an acid is stronger if they have the same amount of oxygen but a different central atom?
Okay, so you're talking about let me get a periodic table that I can use. You are talking about if I have HClO3, HBrO3, HiO3, is that what you're asking me about? Yes?
Yes.
Okay. So remember, what's happening is my electronegativity decreases as I go down the table. Yes? My most acidic substance, if it has the same number of oxygens, yes, the one at the top will be the most acidic.
Okay.
Okay. All right.
Yes.
Did I answer that question?
Yes, thank you. And also I was wondering, what is the difference between a coordinate covalent bond and just a regular covalent bond?
Okay. a coordinate covalent bond, let's look at ammonia. A covalent bond, we talk about sharing, yes?
Yeah.
Yes, we think about that as equal sharing. Here is my ammonia, yes? When ammonia forms NH4 plus. Coordinate covalent bond is where one atom in the molecule donates the 2 electrons. Remember, covalent bonds mean sharing of 2 electrons, yes? And normal covalent bond is 1 atom from each one, yes? That's basically how we tend to talk about it. Does that help?
Yes.
Okay. Good questions. Anybody else?
Hi, Professor. I had a question about something that was in the copyist's book. I can just read it to you.
Okay, tell me the page. If I have the same edition, I probably have it. What?
Yeah, it's page 14-10. It's on the bottom, number 11.
14-10. Okay. Tell me what the question says.
It's basically complete the following acid-base reaction. And for the one number C, which is 10 to
I don't have that question. This is what I have.
14-10.
Oh, that's 11. Sorry. Okay. Which one? That's what I have
Number
on
11 on
I
the
don't
bottom.
have 11. I don't have that one. You have a new edition of the book.
Oh, okay.
Oh.
I mean, I could just tell you.
Okay. Tell me what it says.
Okay, so it's complete the following acid-base reaction.
Uh-huh.
So it's 10 to hydroxide.
SN.
Yeah, SN, sorry.
OH.
SNOH.
That's okay.
And
2
then
hydroxides, yes.
with hydrobromic acid, so HBr. So
Okay.
I was confused on why the OH went on like both sides, because I knew that it was gonna make water, but I just
Yeah, it's
didn't.
gonna form water. Yes.
Right,
Okay.
but I didn't understand
Mhm.
why there was an OH in the middle one too, like in the other one.
Over here.
Yeah,
Let me see if I can find that question somewhere in my book.
I can tell you the answer.
I need to see I want to see the question actually.
Oh, it's just.
Actually, I was talking to Dr. Pappas this afternoon, and I think I know where that question came from. Let's see. It has something to do with the direction of the reaction. Yes, because it tells you when you do the reaction, it will go towards the direction where you have the weaker acid base. So you're going to get SNBr2 plus H2O. Yes, that's what you're going to get.
No, you get
What did you get?
SNOHBr.
Okay.
Yeah,
Okay.
and it's only one arrow, so it's like not.
Okay.
That's why. Yeah.
Okay. And she got SNOHBr.
Yes.
Okay. All right. While I want to explain that question, I can tell you ignore that question. Okay. Because you're trying to test for a final. I would love to explain it to you, but right now let's focus on what's going to be on you need to review on the final. Let me see.
Okay,
I know what it is.
Normally
I know what
I'm
it
used to it like
This is what it
making
is.
water.
This is what it is. You see this part right here? That's what she's doing. Yes. It's on page 14.7, which I did not talk about. Acid salts, basic salts. Yes.
Okay.
That's what she's doing. It just
Okay.
what was going on there.
These are the questions in the back. So I was like,
Yeah, because it concerned this part of it that's
Right.
in the course. Yes. So that's what that is. Okay.
Okay.
So it's talking about basic salts. Yes.
Got it. Thank you.
All right. Okay.
Yeah.
Glad-
And then I also had another question.
Go ahead.
Regarding effusion and diffusion of gases.
Mhm.
If you can kind of go over that, because I didn't really understand that.
Okay, so let's go to gases. Let's just do a summary of gases. Okay, so we have our gases. We have 4 parameters that affect our gases. We have gas laws, P1 V1 over T1, P2 V2 over T2. We have PV equals nRT. I'm gonna get there, baby. Okay, all right. This is constant N. You will use this when they give you information, 2 pressures, 2 volume, or 2 temperatures, yes? You should know for your gas, it's STP is 0 degrees Celsius and 1 atmosphere or 760 torr. Yes? Okay. This is your ideal gas equation, which you should have known. You can use as PV is equal to the number of moles, which is the grams over the molar mass, times RT. So you guys probably learned or studied this equation like this. PVM equals GRT, where you can find your molar mass. Or you could have learned it like this. PV equals PM equals DRT, where the density, this is replaced G over V, where you can find the density of your substance. Yeah. Now, I'm getting to the diffusion portion. Something else you should have learned in gases is you have a mix. You can have a mixture of gases. So if I have a mixture of a couple of gases, let's say I have 3 gases, the number of moles of the gas will be, so if I have 2 gases, A and B, the N in here will be the number of moles of A plus the number of moles of B. Okay, so if you get a question where you have I'm just reading a text, sorry. Okay, all right. So this is how we'd get the total amount of gas if they asked us a question where it involved a couple of gases. Remember, when you do gases, if they say oxygen, is the molar mass of the oxygen is O2. If they say hydrogen, it's H2. If they say neon, it's just Ne. So you have to know how to get there. Okay. Something else about gases. We talked about, let me get the book and make sure I'm saying what I want to say about that. I will answer that question, the student who put that on the chat, okay? All right, so this is one like I was talking about, yes? Where they gave me grams of methane, moles of hydrogen. Notice what they did. They said the pressure is a total number of moles times RT over V. That came from PV equals N total RT. Sorry, my book is messed up. Dr. Pappas needs to give me another book. It's not working out here. Okay, so that's what happened in my book. Maybe you guys, if you guys bought a book and it's like this, you take it back to the bookstore, let them give you a different one. Okay, but anyway, Graham's law. What that is talking about is intermingling of gases or leaking out of a gas. Think about your balloon, your birthday balloon. You buy it in the store. After a couple of days, it's no longer up in the air, it's down. The reason for that is that in that balloon, it's a mixture of helium gas, probably some oxygen, yes, and probably some other gases in there, right? Now, these gases, depending on the molar mass, they move at different speeds, yes? So what the Graham's law says is the rate at which a gas moves is proportional to the square root of its molar mass. That's what that says. The format of your Graham's law that you're using is comparing 2 gases. And that's why, so if I have rate of A over rate of a gas B, that's why we end up with this equation right here. So this is how you probably will remember the equation. What's important is that the rate is volume per unit time. So it's a volume per time. So they'll tell you to do that. They'll tell you like that. Look at this question. It says the rate of effusion of that to that. Remember, your rate is, it's one over the other. Your ratio, it's a ratio. it can be equal to 2 times. So if I said the rate of A over the rate of B is equal to 2, it's saying that my gas A moves twice as fast as my gas B. That's what it's saying right there. Yes? Okay, so that is what that is doing right there. See, they got the ratio and it was 2 over 1. So they said it diffuses through a pinhole twice as fast as SO2. Think about it though. CH4, SO2, the molar mass of this is 16.0, and the molar mass of this is 32 plus 32, 64.0 grams per mole. Yes? Think about it. A heavier gas will move at a slower rate than a lighter gas. I equate it to me. I'm heavy, so my daughter will walk much faster than I can because I'm heavier. You can think about it like that. Doesn't always, it's not always true, but for me it is. Okay, so that is basically what that is. So sometimes they will ask you questions. Look at this one right here. They said 100 milliliters of hydrogen diffuses through an orifice 4 times faster than your unknown gas. Notice what they did? They then wrote it like this. The rate of hydrogen over the rate of the unknown gas is equal to 4. How do you get rid of the, you need to find the molar mass of the unknown gas. So let me do it because my book is messed up. Rate of hydrogen over rate of X is equal to 4. And that's equal to the square root of the molar mass of X over the molar mass of hydrogen. If you get a question like this, this is what you're looking to find. How do you do that? You square both sides. Yes? You square both sides. So if I square this and I square this, I'm going to have 16 is equal to the molar mass of X over the molar mass of hydrogen, H2, which is 2.02. Yes? That's what they did. Yes? So this is the format of Graham's law. You can get theoretical questions on Graham's law. They can give you questions like this. You have a bunch of gases, and I think there's one here. Let me find it. There is a practice at the back of this, isn't there? Final exam questions. Reaction, stoichiometry. Where is my gases? Okay, so here are some questions here on gases. Okay, so if you have this, you can go in and look at the back. Appendix 5 has questions in the back. Okay, so the question that I'm looking for is this question. Number 19, it may be the different one in your book, but it says, which of the following gases under the same conditions would escape more rapidly from an orifice, which is a pinhole? What do we do? What would you do for number 19?
See which one has the largest molar mass.
So the one that would move more rapidly is the one that has the least molar mass, yes?
Yeah.
Yeah, okay. All right, so that's what you do there. Okay, awesome job. Okay, so of course, this is Dalton's law of partial pressure. You should go over that where it says that that's what we were using when I said you had 2 different gases and they are in the container. What is the pressure if you have different modes of gases? So that's kind of what that is. So you can do that. Okay. Did I answer your question? Whoever had the question?
Yeah, thank you.
Okay. All right. You're one person. You didn't cover what in the first half of the semester? You didn't cover Graham's law of effusion and diffusion?
No, Professor.
No. Oh boy.
Professor,
Mhm.
what type of like problems we can get on that on
The
the
test,
gas
anything
chapter?
from this list.
Anything from this list? Okay.
This list is on Blackboard. Yes? Okay, so you said you
Yes,
never
it
covered
is.
Graham's law?
No.
No? Okay, what else didn't you? Okay, so did I say anything in that that you didn't cover? Did you do Dalton's law of partial pressures?
We didn't do any like questions.
Questions. Okay, but the theory part of it, she talked about, right?
I remember she just went in through the chapter, like she read it to us.
She
And
read it.
and I
Okay,
remember
all
like
right. Let's come
doing
down here.
problems.
Let's go to our gases. Here's what it says. Here, yes? Yes, this right here, I talked about that. Dalton's law of partial pressure, all that is saying is that my P total is equal to PA plus PB plus PC, yes? There is another format where we talk about mole fraction, yes? You can go and look that up because I don't have time to lecture on that right now. If I have some notes, I will probably share it with you. I'll look it up and send it to you, okay? But that's what it is, okay? Stoichiometry involving gases. One of your classmates asked me what were the things on exam number 2 that you guys struggled with. One of the things I looked at the questions, it was stoichiometry involving gases. It was this section right here, which was this section right here. Yeah, 15, 16, 17. Yeah. Okay, it was about redox reactions as well. Okay, so anybody has any questions for me? Any other questions? Looking at this list, I know some stuff is kind of rusty here, but looking at this list, let me do it on the computer. It's probably going to pop up a little bit better. There we go. You tell me what you'd like to look at. Let me zoom it in a little more.
Would you cover one redox reaction?
Okay, so you will just give me the list so I know what I'm doing. So let's look at this, guys, and see what you want me to talk about, and I will just go forward. Redox reactions. So you're talking about balancing an acidic and basic media, correct?
Yes.
Yes.
Okay. All right.
And can you also cover a little bit of the base?
The base
bases.
reactions. Okay.
Yes.
All right. Okay. What else? So you have had a chance to look at that. 1 minute. Okay. Let's move it. Oh, moving the wrong thing. I'm moving the one on my dock camera here. Okay. All right. So let's see. Is there anything else on there that you probably want? I came in and we started talking about electronic configuration, electromagnetic radiation, formal charge, Vesper, valence bond theory, acid-base theory, right? So what she did was number 42. So you're asking me to look at 42. We did a little bit on 43, 44, 45, 46, 47, 48. Yes? Okay.
And 38.
38, MO theory. Yes.
Yes.
I will mention that. I think you probably will have only 2 questions on that, but I will mention that. Okay. Anything else, guys?
Professor,
Hmm?
for electromagnetic radiation, do we need to study just like the formulas, or do we need to know the concepts too, like what's wavelength and frequency and stuff like that?
Well, you could get a theoretical question like the relationship between frequency and wavelength, stuff like that. But most times the questions are calculations. Yes. Okay.
Yes, and I have another question because you didn't list the net ionic equations there, but you talk about them last class. So I just want to make sure if they're gonna go.
Okay, where is it? It's here.
No.
complete, this is what it is. It's covered in this section, 16, 17, 18. Yes?
Oh,
Complete and balanced double replacement reaction, which means total ionic equation, net ionic equation, spectator ions. That's what that section talks about. So 15, 16, 17, 18 is a section where you do your double replacement reactions, your single replacement reactions. That's what it is. Yes? We
Okay.
need help with that?
Mm,
Identifying, oxidizing, reduce. Okay, so let's go. So we're going to talk about redox, right? Okay, so let me get into my chapter here, find me a question, and we'll go. Okay, chemical reactions, redox. Okay, so I'm going to show the book. Okay, so you can be asked, okay, you can be given an equation and you can be asked to balance it, yes? And it's going to be a multiple choice, so we'll probably ask you, what is the oxidizing agent? What is the reducing agent? Or we can ask you to balance the equation and tell me how many H plus ions balance the equation and which side it's on. You guys had some questions that I share with you all on Blackboard. I'm trying to find it here. I think I have it open up. Let's see. Okay, not that one. Just 1 second. I think I opened it up. I shared some questions with you guys, and I thought that was there. I don't find it. So, okay. It's not there. So anyway, how do we do that? Let's say they gave me this reaction here. Are you guys seeing it? So I'm gonna start doing it for you. So they gave me this on the test. MnO4 minus plus SO3 2 minus MnO2 plus SO4 2 minus. And they say balance under basic conditions. Yes? Or basic medium. And they ask me, what are the sum of the coefficients when I balance the equation? So what am I going to do? Let's review balancing a redox reaction. This is how I do it. I'm going to separate into halves. MnO4 minus MnO2. SO3 2 minus SO4 2 minus. You do this. The first thing you do, so this is my equation number 1 and my equation number 2. I look at all atoms except hydrogen and oxygen and look if it needs to be balanced with coefficients. So there's nothing there. 1 and 1. Then I look at my oxygen atoms. I have 4. I have 2. I balance my oxygen atoms with water. So I'm going to put 2H2O here. Then I'm going to look at what I just did and balance the hydrogen atoms that now exist in this. I have 4 hydrogens. I have none on the right and reactant side. So I balance my hydrogens with H plus. Then I will balance for charge. This is 4 positive, 1 negative. On my reactant side, I have 3 positive. It's 3 positive. On this side, it's 0. I balance for charge with electrons. So I'm going to add 3 electrons. You know where you can find this if you're doing labs? Go to experiment 13 in your lab manual, and it will explain in detail exactly what I'm doing here. Okay, experiment 13 in your lab manual if you're doing labs at Kendall. Okay, so that's my balanced half equation for the first one. This is a balanced half equation.
Professor, where do you get that 3?
Okay, I got the 3 Thought I brought a whiteout down here. I guess I didn't. I got the 3. Let's back up. You saw that, correct?
Yeah.
Okay. So now when you balance the redox, you have to balance for atoms and charge. You balance for charge with electrons. Before I did that, the product side has 0 charge in this particular half equation. In this, I have 4 positive, 1 negative. Remember, the 4 multiplies that, right? So the reactant side has a 3 positive charge. Yes?
Got it.
I can only balance with electrons. Yes? So when I put 3 electrons there, this now becomes 0 charge on this side. Yes? Are we there?
Yeah, I got it. Thank
Go
you.
to experiment 13 in your lab manual. You'll see it there. Okay? And they explained it in detail. So we are balancing. When I balance my halves, we're balancing under acidic conditions. To balance under basic condition, you need to balance under acidic conditions first. So let's come here. Sulfur, sulfur, 1 and 1. So I don't need to put a coefficient for that. 3 oxygens, 4 oxygens. So I need to put a water on this side to balance my oxygen. Now I'm going to look at what I have here. I have 2 hydrogens. I have none on the product side. You balance hydrogens with H plus ions, 2 hydrogens. So I'm going to put 2 H pluses here. Yes? Now I have to balance this one for charge. The overall charge on this side is 2 negative. Yes? The overall charge on this side is 0. I can only balance with electrons. If I put the electrons on this side, it's going to still be negative. So I need to add 2 electrons on that side. This is my balanced half equation for SO3 2 minus going to SO4 2 minus. This is the complete equation. So we said we have to add them together. In a redox reaction, my electrons are not visible. They are invisible. Yes? They don't show up. This is a redox, oxidation reduction. Remember, oxidation is loss of electrons. So this is an oxidation reaction where when the reaction takes place, it produces electrons. When reduction is a gain of electrons. So this is my reduction half reaction. And this is my oxidation half reaction. So I want to get back here. This one needs 3 electrons. This particular species only giving up 2 electrons. So we tell you, you need to multiply by a factor. So if I multiply this one by 3, I will have 6 electrons. If I multiply this one by 2, I will have 6. I'm going to rewrite it again. So we have 3 electrons plus 4H plus MnO4 minus. I'm going to multiply this one by 3. I'm going to multiply this one by 2. And I'm going to add them together. When we do that, I get 6 electrons plus 4 2s, 8 H pluses plus 2 MnO4 minus. That's on this side. Down here, I got 3 waters plus 3 SO3 2 minus. That's all on my reactant side. Did I do that right? Yes. On my product side, I got 2 MnO2 plus 4 H2O plus 3 SO4 2 minus plus 6 H plus 6 electrons. That's what I got. We are going to remove spectators. Yes? When I add my two together, my electrons become invisible. There's 6 on this side, there's 6 on that side. Let's see, what else do I have? I have H pluses on both sides. There is 8 here and there is 6 here. I'm gonna get 2 H plus left over on the reactant side. MnO4 minus, that's the only thing that's there. Water, I have 3 here, I have 4 here, so that's gonna be gone, and I'm gonna have water on this side, 1 mole of water. 2 MnO2 is gonna remain there. SO3, okay? And of course, I'm gonna have my 3 SO4 2 minus. This is my balanced equation under acidic conditions. Let's see if it's balanced. You know it's balanced, so if they ask you to balance on the acidic and they say, how many H pluses are in the reaction? 2. Which side it's on? The reactant side. So let's see. We have 2 hydrogens, 2 hydrogens. We have 2 manganese, 2 manganese. We have 3 sulfur, 3 sulfur. We have 2 4s, 8, 8 plus 9, that's 17 oxygens. I have 4, 5, 5 and 12, 17 oxygens. Charge. On this side, I have a total of 3 times 2 negative, 6 negative charge. On the reactant side, I have 3 to 6 and 2 8 negative, 2 positive, 6 negative. So that's how you check your equation if it's balanced. So this is under acidic conditions, yes, or under acidic medium. But Professor, you said basic. So if you know how to get your acidic, you can get to basic. When you have your balanced equation under acidic conditions balanced properly for basic, you add OH minus for every H plus present. So what am I saying? If when I had finished this, I did not have any H plus in my reaction, I wouldn't need to add any OH. The equation is balanced, so I add OHs to both sides to keep it balanced. Okay, so to do this, I see H plus here. So I will need to add a OH for every H plus. Why? Because H plus plus OH minus gives me water. So let's do this. 2H plus plus 2 MnO4 minus plus 3 SO3 2 minus 2 MnO2 plus H2O plus 3 SO4 2 minus. They want me under basic, so I see 2 H pluses. So I'm gonna add 2 OH minus to both sides to keep it balanced. Bearing in mind that this gives me water, I'm gonna have 2 H2O plus 2 MnO4 minus plus 3 SO3 2 minus. All I'm doing is writing down what I have. 2 MnO2 plus H2O plus 3 SO4 2 minus plus 2 OH minus. This is technically my balanced equation, but guys, I'm looking here and I see something I can simplify. So my balanced equation for this reaction is, I'm gonna get rid of that. I'm gonna have H2O plus 2 MnO4 minus plus 3 SO3 2 minus is going to give me 2 MnO2 plus 3 SO4 2 minus plus 2 OH minus. And this is under basic conditions. Okay, and I'm going to find you the answer so you see that I did it properly. This was 3F. 3F, H2O, let me get my paper, plus 2M, plus 2MnO4 minus, plus 3SO43 minus, where are we? Right there. Yes? Okay. Gives me 2MnO2, 3SO42 minus, 2OH minus. The exact thing there. Okay. So that's how you will balance. And as I said to you guys, if you're doing labs at Kendall, go to your lab manual. It shares with you how to do this. Yes? Okay. What else? I was supposed to have a list. I think I lost my list. So let's look at this equation right here. Let's just look at this equation. Let's pretend they just gave me this equation. Or let's pretend they gave me just this equation. MnO4 minus plus SO3 2 minus MnO2 plus SO4 2 minus. They ask me, what is oxidized? What is reduced? What is my oxidizing agent? What is my reducing agent? I will just tell you this. You know what oxidation is. Oxidation is increase in the oxidation number or loss of electrons. If you never knew that, if you think of Fe2 plus to Fe3 plus, that's oxidation. It's going from iron 2 to iron 3. How did it get there? This is at the oxidation number of your ion is a charge. Am I correct? Yes? I've lost you guys. Are you still there? Are you guys still there?
Yes.
Okay. All right. So this is how I thought about when I did my chemistry. I had to remember oxidation reduction, right? So I thought of oxidation as iron, Fe2 plus to Fe3 plus. How is this equation balanced? No. How can I balance it? Put an electron. Yes. So this was Fe2 plus is oxidized, and it's oxidized by loss of electrons. Reduction is the I talk it like the opposite or the reverse of oxidation. So my reduction is a decrease in the oxidation number or gain of electrons. Yes? So I don't have to go there. I just focus on one. Yes? Now they'll ask you, what is oxidized? They can give you this and ask you, what is oxidized? Guys, this is not the question on the test. I know you didn't understand this, so that's why I'm doing this. There's something on there about it, but not this exact question. Okay? So how do you find what is oxidized? What is oxidized? You're looking for something where it either changes its oxidation number, because in this you don't see any electrons. So you're going to look for change in oxidation number. Remember you learned how to do oxidation number? Remember that? Remember how to do oxidation number? Oops. Okay.
Yeah.
All right. So let's do oxidation number. Yeah. So we're going to look at the oxidation number of Mn here and Mn here. So we're going to do MnO4 minus and MnO2. What's the oxidation number of my Mn in here? We know that oxygen is -2, correct? So the oxidation number of this, you don't have to write it down. 4 times -2 is -8, yes? The oxidation number of an ion is equal to the charge. So 1 times the oxidation number of Mn plus 4 times the oxidation number of my oxygen should be -1. That's how you do an ion. So I don't have to write it all down. Oxygen is -2. 4 times -2 is -8. This has an overall charge of -1. So what is this? +7. Yes? Are you guys with me? Questions? I know I'm going fast. Let's come here. What's the oxidation number of my Mn here?
8.
8.
How did you get 8?
I equal to 0, and then it'll be like x, exactly, like plus
Yes,
2
this is 2
times
times
negative 4.
negative 2. It's not
Minus
4.
Exactly. Oh, right.
Ah,
It'll be 4.
oxygen.
It'll be 4. Right.
Plus 4. Yes? Yes? So what happened when this went from MnO4 minus to MnO2? Your oxidation number went down. Yes? Number line, plus 7, plus 4. Yes?
It reduced.
It was reduced. Yes? So my MnO4 was reduced. Yes? Whatever is reduced is your oxidizing agent. Species reduced is the oxidizing agent. Do I have to write the other part? So species oxidized is the reducing agent. Yes? So in this particular equation right here, we only have 2 reactants. Yes? Oxidation reduction occurs together. Yes? So if this is reduced, what happened to this? What happened to my SO3 2 minus? It was oxidized, and we can prove it. Oxidation number of my sulfur here. Can somebody help me? Oxidation number of my sulfur here. Okay, I guess this is where the lecture stops. The help stops, but I'm not going to tell you.
5.
Is
Okay,
it,
say that again?
is it 4?
Yes. Didn't I just share with you? If you have the charge, each oxygen is -2. 3 times -2 is -6. This whole ion has an overall charge of -2. So my sulfur had to be +4. What is the oxidation number of the sulfur in the SO4 2 minus?
6.
+6. Yeah, when we talk about oxidation number, we use the plus sign. Yes? So what happened here? It increased. Yeah, so you notice we're going one way. I wish you could see my hand. That's why I like face-to-face classes. Yes? Redox. Opposite. So that's why we don't see the electrons. Are you with me? Whatever
Professor,
go ahead.
so as an example, if we
Mhm.
have a question and they give us the equation like that, if they ask us what's oxidize and reduce, we can use this trick.
You can, it's not, if you call it a trick, go ahead.
Yeah,
I mean,
yes,
I'm just helping you guys. I don't know if it's a trick. If you call it a trick, go right ahead. Okay.
No, because it makes sense. Like instead of doing all of the process we just did to find
If
the
they didn't ask you to
equation.
balance it, you don't have to balance it. I'm trying to
Oh.
find the thing that I got. I share with you guys. Let me see if I
Thank
can.
you, Professor.
Okay. I'm trying to see if I have one on here. I know. Okay. All right. So I'm gonna share. Where is this one? Where's this one? What's the net ionic? Okay. I guess I'm gonna be here very late tonight. But anyway, all right, it's fine. If you can stay, I can stay. Okay. So let's look at, where was the one I was just looking at? Look at number 12 on this one. It says, how would you do number 12 if you got that? How would you do that? How would you do number 12? Any ideas? Talk to me, guys. Let's test your knowledge. How would you do number 12? It says, which of the following chemical reactions are oxidation, reduction reaction, or redox reaction? What we just did, we just said redox, right? Oxidation, reduction. One is going to increase its oxidation number, one is going to lower its oxidation number. We have no electrons in here, yeah? So what am I going to do? I'm going to look for something that had changed its oxidation number, yes? Okay, so if you look at this, did magnesium change its oxidation number? What's the oxidation number of a free element?
0.
What is it in the compound? The charge.
2.
What's the charge in here of the magnesium in this compound? The magnesium in this compound. What's the charge of the magnesium in this compound?
It'll be 2, right?
2 plus.
Plus 2, yes?
Yes.
It was 0 here. It was plus 2. So what happened to my magnesium?
It increased.
The oxidation
It
number
decreased.
increased means it was
Oxidized.
yes?
Yeah.
If you got a question like this, guys, if there is a species in the equation that was oxidized, reduction also take place because oxidation doesn't occur without reduction. Are you guys with me?
Yes.
So if you get a question like this, you need to look for a species that you can see where the oxidation number is different on the reactant side from the product side. I can tell you in all the others up here, yes, the oxidation number of my carbon is +4 in this one, it's going to be +4 in this one. My hydrogen is +1, it's +1. My oxygen is -2 in a compound, it's -2. You don't see a change in oxidation number of any of the elements here. This is a double replacement reaction. Number B, am I right?
Yes.
Okay. Double replacement reactions are never redox reactions. Double replacement reactions are never redox reactions. Okay. This equation number C is a neutralization / double replacement reaction. Am I correct?
Yes.
Yes? Okay. So if you go in and you check the oxidation number of the hydrogen, the sulfur, the oxygen, the barium, it's going to be the same on both sides. Yes? Okay. And if we come down here, we see it's going to be the same thing for D. So to get you out of what we were talking about, when you're asked what is oxidized, what is reduced, that's how you do that. Whatever is undergoes oxidation or change in its oxidation number, that is a reducing agent. Yes? Okay. All right. So since I'm here, this was one of the topics where you all had issues in the exam number 2. At least every time I looked at a question like this in exam number 2 for you guys, hardly anybody got it right. So let's look at number 10, net ionic equation. Yes? Anybody has an objection to that? Or you have something else pressing you'd like me to look at? Talk to me, guys. Come on.
The molecular orbitals.
Okay, I'm going to do that. I promise. Okay. If it's the last thing I do, I'll do that. Just remind me at the end. Okay. Net ionic equation. Unfortunately, I don't have that printed, so I'm going to talk. It says acid-base reaction of sodium hydroxide reacting with a solution of H2SeO3. That's selenous acid. Okay. So they're asking me to get the equation. So these are my two reactants. An acid and a base, yes. So we know we're going to get water, right? So we're going to get HOH for sure, and that's a liquid. And we're going to get the compound between sodium and the selenite ion. This is a -2 charge. I know that because it has 2 hydrogens. So I'm gonna have Na2SeO3. I have to decide on the states. And my solubility rules tell me all alkali metal salts are soluble. So this is going to be AQ. I will need to balance this before I can go to the net ionic equation. So I need a 2 here. Yes? So this is my molecular equation. I need to go to the total ionic equation before I do the net. So I'm going to go over total ionic equation. To get the total ionic equation, you need to use your balanced equation and write as ions strong electrolytes. What are strong electrolytes, guys? Strong acids. The 7 that we talked about. Strong bases. Soluble salts. Yes? This is not a strong acid. So because it's not a strong acid, I leave it in its molecular formula. So we are going to get 2Na plus, because I have 2 moles, so I'm going to get 2 sodium ions plus 2 OH minus ions. Plus, even though this says AQ, it's a weak electrolyte. No, you're kidding me. Okay. All right. I have 10 more minutes. Okay. And so I'm going to write this like that. I'm going to come to the other side. Water, liquids are left. So I should have had a 2 here. I'm so sorry. I should have had a 2 here. Yes. 2HOH. This is a soluble salt. 2Na plus SeO3 2 minus. That's my total ionic equation. My net ionic equation, I am going to take out spectator ions. Do we have any more spectator ions in that one? No. So it's 2OH minus plus H2SeO3 to give me 2H2O plus SeO3 2 minus. And that's the answer we're looking for. Let's see if it's there. Where was I? Okay, I don't know which one I was looking at. There we go. Do we see that one there? I think it's D. Yes? D is the one that I just wrote. Look at D. Look at what I have here. Only thing is remember, it doesn't matter the order in which you write them as long as they're on the product side, reactant on the product side. Yeah? So that's what that is. Okay? I can share something with you about this, but let's see. So this was my molecular equation A, C. You should have been told or shown that this ionic equation, C, will always result if you have a strong acid, strong base reaction. In the one I just did, that's a strong base with a weak acid. So that's why I did not get that. Okay, so that's what that is. I'm going to answer your classmates' question about molecular orbital. And the only thing I'm going to share with you, remember I said we didn't have to do a lot on that because, let me find it. What we need to know about molecular orbital theory, we need to know that when we have overlap of orbitals, if I start out with 2 atomic orbitals, I get two molecular orbitals. Okay, one that is a bonding and one that is anti-bonding. See what it shows us right here? Yes, I get a bonding and I get an anti-bonding. Okay, that's what I get. Your anti-bonding, when we give it to you, it's going to be the star. Okay, that's what we get. So that's how we know that. We also need to know that when we overlap or p orbitals, yes, we have three p orbitals. Let me see if I can quickly share that with you guys. If you need to go, you can go. I will stay and answer questions for a little bit longer. Okay, but if you have, remember when we have p orbitals, right? Remember we have three p orbitals. We have px, py, pz. Remember when we had the orbitals, we said they were dumbbells, yes? And we have three-dimensional, so that's basically what we have. So if I have orbitals from two atoms, two different atoms, px, py, pz. When my three orbitals, so here I have 6 orbitals coming together. One set is going to give me sigma. Yes, so my overlap of my p orbitals will give me sigma bonding, anti-bonding, yes, and 2 pi orbitals. Here's what it says. Depending on whether all p orbitals overlap, there can be as many as 2 pi's, but only 1 sigma. Remember when we did my valence bond theory, we talked about pi bonds where we had side-on overlap? The same scenario is happening here. Okay, so overlap of my p orbitals and molecular orbital gives me sigma bonds, sigma bonding orbitals by head-on, and side overlap is going to give me molecular orbitals. I mean, pi molecular orbitals. The main thing you guys need to know other than that is about bond order. Yes? Bond order, the number of electrons in the bonding orbitals minus the number of electrons in your anti-bonding orbitals, divide by 2. It also says bond order corresponds to the number of bonds that we saw in valence bond theory. We saw that a triple bond was a stronger bond than a double bond, which was a stronger bond than a single bond. We will see in this that a triple bond will have a bond order of 3. A double bond will have a bond order of 2. A single bond will have a bond order of 1. We can have fractional bond orders. The greater the bond order, the stronger the bond. And remember, my triple bond was shorter than my double bond. Shorter the bond. There is a lot more to molecular orbital, but that is all we want to share with you at this time. Did I answer your questions? If you're looking at molecular orbital and you have the Papa study guide, it's module 13. Yes? Okay. So how do you get bond orders? They're going to give you, let's look at this question. Something like this. They're going to give you a scenario written like this, yes? If they give you a scenario written like this and they say, what is the bond order? You look here, the bond order. How do they get this? They add the ones without the star. 2, 4, 6, 8, 10. That's how they got the 10. Minus the electrons in the anti-bonding, which is the ones with the star. 2, 4, 5. Divide by 2, and they got 2.5.
So this is the, sorry, Professor, this is the type of exercise like problems we're gonna have on the exam for that chapter.
You can make your conclusion.
Okay.
Professor, so we're not gonna have the actual diagram where we put.
I don't think I'm gonna put the actual diagram. If I put the actual diagram, let's put it this way. If I put the actual diagram right here, yes? If I give you the actual diagram, yes? Let's say I ask you what's the bond order of He2. I would give you this diagram, yes? What would you do? 2 electrons in the bonding, yes? 2 electrons in the anti-bonding. You see that?
Yes, I just don't understand when it becomes pi. When it
becomes pi.
Yes,
okay?
when it becomes larger than that is when I got confused.
Okay, so let's see if I can put some pencil. Okay, so let's see if I had it here before. So this is probably 1s2, 2s2, 2p5. So that element is fluorine, yes? So I'm trying to do the molecular orbital for F2. That's what I just wrote here, yes? This is fluorine, yes? And that's fluorine. So when I'm doing that, 1, 2, orbitals get filled like they normally do, yes? 1, 2, 1, 2, 1, 2, 1, 2, yes? So I have a total of 5, 10, yes? 2, 4, 6, yes? Do you see that? I've used all my electrons, haven't I? Two, 4, 6, 8, 10. 2, 4, 6, 8, 10. Yes? You seeing what I just did? I'm not going to ask you to fill it in. I could, but I'm not going to go there. Yes? So they ask me I give you this diagram on the test, and I ask you, what is the bond order of this molecule? What am I going to do? My bond order is going to be 2, 4, 6, 8, 10. Yes? Minus 2, 4, 6, 8. Yes? Divide by 2, 1. F.
Okay, I see it now.
Yeah? So
Yeah.
what kind of questions? You can get a picture, and you're just giving me an idea, okay? I can give you a picture, or I can write it like this. Yes? This here came from this. So I don't have to give you a picture. I can give you the shorthand notation. Yes?
Yes.
Okay. All right. Next question.
Professor, can you cover really quick polarity of molecules?
Okay. Okay. Like what? What do you want me to do? Help me out a little bit so I can go a little bit quicker. I would love to do with you guys review this as well, because that was a concept in your exams that you didn't get. But polarity of molecules. Okay. So we draw Lewis dot structures, yes? And we talk about polarity of molecules. So I can do CH4, I can do NH3, I can do CO2, I can do HF, yes? Okay, so for my polarity of molecules, excuse me, remember your polarity of molecules, your molecules involve bonds, yes? So we can talk about the Lewis dot structure and all that stuff, right? So technically, I'm just gonna draw my Lewis dot structure like this. Yes? For you to have a polarity of a molecule, you have to investigate the bond. I'm going to do the devil's advocate here. Yes? So I need to look at the bonds. Remember, this does not tell me the shape of the molecule. Polarity of molecules depends on the shape of the bonds. But to do this, we can look at this. Here we go. I have atoms with different polarities. So this is a polar bond, a polar bond, a polar bond, a polar bond. Yes? When I look at a molecule with a central atom and all the atoms on the molecule, on the central atom are the same, yes? And there are no lone pair electrons on the central atom, that molecule is going to be nonpolar. Let me say it again. If I have a central atom, or for example, SF6, if I put all my dots, I have no electrons on the central atom. It's going to be a nonpolar molecule, but it has polar bonds. What's a polar bond? It's basically, where's my periodic table? With a separation of electronegativity, yes? The only time you're gonna have a nonpolar bond is if you have F2 or H2 or O2. That's technically the nonpolar bond. Okay, so let's look at this. So this is a nonpolar molecule, but it has polar bonds. In this situation, I have polar bonds, but because there is a lone pair on the central atom, electrons pull. So my electronegativity is going to be pulling in that direction, yes? So this will be partially positive, and that will be partially negative. Remember, polarity is a separation of charge, yes? So this is a polar molecule. Did I lose you guys? Are you guys still there?
Yes.
CO2, look at CO2, a polar bond, a polar bond. There is a line of symmetry, yes? So we have polar bond, non-polar molecule, yes? HF, we know that this is a polar molecule because my fluorine is the most electronegative, so it pulls the electrons in this bond towards itself. So we have, that's what we have. Okay, if you have the Papa's book, I can tell you where you can find that. If I remember, it's in chapter 12. Sorry, module 12. Remember me showing this in class? Anybody remembers me showing this? Yes? Yes?
Yes.
This was when we did Vesper, but that's basically what it's talking about. Yes? Okay. All right. So that's how you want to look at polarity of molecules. I know many people have left, but I wanted to share with you. The faithful few might find this useful. Where's my paper? I printed it. Please tell me I know where it is. Summary of reaction stoichiometry, guys. Have you ever seen something like this before? Oh, it's not going to show. Okay, this is my summary of reaction stoichiometry, right? Remember grams to moles to grams, yes? If you have density, you have volume, yes? You go in, you come here, yes? Reaction stoichiometry with solutions, it's just different ways of getting the number of moles of the reactant or product, yes? So you can come here. If you have a gas, you do this, and you come in, and they can ask you about the pressure, volume, temperature of the gas if you produce another gas. So this here is a summary of reaction stoichiometry. Remember, molarity is moles per liter. They can ask you to find the molarity of a substance or how many grams of the substance that makes a solution. There were questions like that on your exam. Can't remember if it's 1 or 2. Yes, they can give you particles to go to moles. You guys should know about that. Yes, okay. So this is my summary of reaction stoichiometry. Okay, so you should know how to do any question involving anything right here. Go in density, go for it. Now, the reason why I share that, a limiting reagent. Let's look at limiting reagent. Remember, if you have a reaction, limiting reagent, if they give you the amount of 2 reactants, you have to decide which one it is. You don't just look at it and say, oh, it's the least amount they give you, that is the limiting reagent. You have to do a reaction stoichiometry problem, which means taking it through this. Okay, that's what that is. Okay, now, you should know about percent yield conversion. This is what I want to say. And I think I had a question on there. They will tell you that you have molarity. If they give you a solution with a certain molarity and they ask you what is the mass percent of the solution, did Professor Minsal do that with you guys? Or they give you mass percent and they ask you to what is the molarity? Did she do that with you guys? I think I saw one on your test actually. Let me see if I have one here. Okay. Nope, it's not there. Let me just go to the book. I think I have one in the book. That in the book is here. It was done in here. I think I have an old book right here. I don't know where my other book is. It's called interconversion of units. Yes, to go from molarity and weight percent or vice versa, the density needs to be known. So let's look at this one. Yes, remember what specific gravity is? It is the density. It's basically saying that 1 milliliter of the solution is equal to 1.84 grams of solution. So if they give you your molarity and ask you to go to mass percent, it's like a fractional conversion. Yes, so what are we doing? My molarity is moles of my H2SO4 per liter of solution, and my mass percent is grams of H2SO4 per 100 grams of my solution. Yes? Or over grams of, or I can write as grams of solution times 100. So if they gave me the molarity and they asked me to ask me about the mass percent, it's fractional. To do a fractional conversion, you take this and you do that, you get an answer. You take this and you do that, you get an answer. You divide the two and multiply it by 100. This is the density that connects it. The connection between grams and volume, it's the density, because your density is mass over volume. I'm trying to find one on here that I know it was here. I guess not. Okay, so let's see. My book is all messed up, but see, it says what is the weight percent of a solution that's 14.7 molar H3PO4 has a specific gravity. So this is what they did. They took this, which is the same as 14.7 moles in 1 liter, and you're going to mass percent. So what did she do? She took the numbers to convert from moles to grams and put it on the top. Molar mass, yes. and she took the bottom. This was supposed to be a multiply, and she did the converted the milliliters, the 1 liter, which is 1,000 milliliters, to grams, and then she multiplied it by 100, which is basically what I said right here. Yes. So if you are asked to go from molarity to mass percent, you do that. If it goes the opposite way, you do the opposite thing. Because if they gave you the percent, if they said it was 12.5%, that is the same as 12.5 grams of X in 100 grams of solution. And they're asking me for the molarity, which is the moles of my X per liter of solution. I'm gonna do the same thing. Take my grams to moles, take my grams of solution using the density. Yes, and I can get my answer. So that is what that was. Okay. All right. So I think I did what I thought I wanted to review with you guys. You didn't come with any questions. This is what you are going to get on the test. You're going to get the periodic table. You're going to get your electromotive or activity series, and you're going to get your constants. Okay, so this will be on the test. Yes. I will share with someone in my office. You know, you want a physical periodic table, and I told her to remind me. I can't remember if I did it or not. So you want to look at.
I was about to tell you, Professor.
Okay, so I will share this with the faithful few who are left. So you have something, you need a periodic table. Man, I don't have a periodic table. I don't have a physical periodic table. You're seeing this. Your periodic table basically looks like this. Yes? You can use this to memorize your trends. Yes? They give you something. They give you CL, they give you BR, they give you BR is under there. They gave you SI, they gave you AG over here. Yes, you can figure it out. You don't have to have that. Am I making sense? You look at your periodic table on the computer, you have blank paper, you sketch your periodic table. Let me do it a little bit better. Give you more space, yes? And if you have to do a trend, you look at your, oh, my CL is over here, CL is right there, my BR is right there, my silicon is over here, yes? My sodium is over here, yes? So that's what we'll do, yes? Okay? And we can do our trends like we do. So if you have all these trends bubbling up in your head, test starts, you draw this on your blank paper and you start jotting down what you need to jot down. You showed your paper was blank, so guess what? This is when the test was being done. I think I said that last time to you guys. Okay. All right, so I will go ahead.
I have one question, but it's a dilution.
Dilution, okay. What about it?
It's in the book. It
The one I'm looking at?
Yeah.
What's the question? Page number, maybe I have the same question.
Well, okay. You said I have a different book than you, so.
Let me know, tell me the page. It might be the same, depends on what it is.
It's in the end, so it's A5-4.
Okay, so it's in the appendix, so it's in the in the review.
Yeah.
Okay. Tell me the question.
Number 12, it says you could prepare a 0.600.
Right there? This one?
Yeah, that one.
Okay. So remember your dilution is your dilution is, where are we? Here, right? M1V1 equals M2V2. Yes? You get the same number of moles when you dilute. You haven't changed. Remember, the number of moles is your solute. You haven't changed anything. Okay? So it says you can prepare 0.65 molar by diluting 6.60 molar. So it's 6.60 molar, gonna give me 0.65 molar times a certain volume. Yes? The only way you can answer this question is to plug numbers in. You have to plug the numbers in. So if you would happen to get a question like this, you have to plug the numbers in. And what do? You put 39.6 and you put 442, yes? When you multiply them, they should be equal, yes? And that's how you find the answer to that one. There's no other way to do it.
Oh, you have to just put it, okay.
You
alright.
have
My
to
internet
try.
went out for a second, so I was kind of confused.
You have to try, yes?
Okay, okay,
Okay,
thank you.
all right. Any other questions? I'm winding down now. I am out of energy and everything else. But good thing it's still recording. Anyone else? So I was saying that I will offer you guys office hours on Thursday. I will send an email out. If I don't, will someone please remind me? I will open up my office hours between Thursday. Between 2 and 4 o'clock. Okay, so if you need something, normally office hours is 4:25 till 5:20. I'm opening. I will be in my office room between 2 and 4 o'clock. If I'm not there, you come there, send an email, and I will get back in there. Okay, because if nobody's there, I'm gonna leave. Okay, so that's what that is. Okay, so with that, I'm gonna stop the recording. Where's it? Stop and share. Stop recording.